Okay. Let's get started. We want to finish up aggregates today, and also have your graded exams, which I want to return. You have a chance to look at it. So that's the plan. Let's remember where we left off last time. We were talking about gradation, sieve analysis. The way you do it is you stack a number of sieves starting from the larger sized openings to the smaller size, and you leave the material on the top and you shake it up with a system like that, like vibration, and you basically look to see how much is retained on each sieve. And once you have that, you get a gradation curve, which is semi-logarithmic. And the last thing we talked about was this sieve analysis, where you have the weight retained and then cumulative weight retained, then percentage. You could change the order actually. And then when you subtract it from 100, you get percent passing. And there are a few things you can extract information from gradation curve. For example, maximum aggregate size, which is the smallest sieve size where everything is passing through. And this was, I think, the last thing we did. We drew this gradation curve together. So for most of the applications, we want to have gradation curve which is continuous and smooth, because you don't want to have too much voids in asphalt concrete or in concrete. You want the finer aggregates to fill up the space between larger aggregates. It turns out that the maximum packing, so if you want to have the maximum packing, it means that the ideal situation where if, for example, you had a certain container, if you have this kind of gradation, you will have the maximum weight or minimum. Is there any question? Any questions I could answer? Or minimum void? And it turns out that the relationship is like that. So to get the maximum packing, basically the percentage, the theoretical percentage is 100 times the sieve size. And this is the maximum sized aggregate. So here 25 millimeter is the maximum. So you have 100 and then you get other numbers. And if you have that, if you have a gradation which is represented by this relationship, this is the densest you can have. This is called 0.45. So you saw that here there is a power 0.45. This is called 0.45 power graph. So if you plot percent passing versus sieve size to the power of 0.45, the densest is basically the maximum packing. But this is a very ideal situation. We don't live in an ideal world. So typically, our gradation would look not like that. So if you look at really a 0.45 power graph, so this is size to the power of 0.45 again, the densest is this line that we just talked about. So here the percent passing, as you saw, it's like 100 di over d to the power of 0.45. That's the ideal, the densest that you can have. This is di. And this is d. So, but typically we have one of these other situations. For example, the one that you just worked on looks like an open graded aggregate. This open graded, if you look, for example, you see that after a certain size, the person passing becomes very small. So after a certain size, so you look from here, you see that there is very little going through the very small sieves. What does it mean? It means that the amount of fines are missing. It's open. You have a lot of void, larger voids. The extreme case of that is the one which looks completely like vertical. This is pretty much, you have one-sized aggregate. It's like you buy marbles. The gradation would be vertical like that. Everything passes through one sieve, and that's it. How about the gap graded? Can someone explain this graph? What does it mean, gap graded? What does this graph tell you? Let me put some color on it so you see it. If you see this gradation curve, what does it tell you?
You're missing some sizes.
You are missing some size. Which sizes exactly?
The mid-sized ones, it looks like on here.
What do you see in gradation curve that you see that? What's the characteristic? Exactly. So in the gap graded, where you see the horizontal lines, that is when, let's say here, between this size and this size, the person passing doesn't change. What does it mean? On those sieves in between, nothing is retained. There is nothing. So those are missing. That's why it is called gap graded. Right? Also on the top, you see there is a section like that. It's very important that when you look at a gradation curve, you can interpret it. You understand what's going on. Plotting it is not very difficult. It's important that as an engineer, when you look at it, you kind of understand what it means and what type of gradation you are looking at. Any questions on this? So this one kind of summarizes what I just told you, so you can go back to that. And now we go through a number of important things related to gradation. One is a definition called fineness modulus. This is a definition, and it's used for concrete mix design. So that's why we care about it. And it is the cumulative percent retained on sieve sequence. You have the sequence numbers. So basically, whatever retained in percentage on these sieves, you sum it up divided by 100, you get a number between 2 and 3, and that's called fineness modulus. Question: if it is larger, is your material finer or coarser? Is it finer? You should try to explain to me why, with the justification. This is the kind of questions you should expect. So the question is, what does it mean? Fineness modulus. If it is larger, what does it mean? We are talking about fine aggregates. All of them are smaller than number 100, so they are not large aggregates. But among those, what does it mean? If you have a fineness modulus of 2 or 3, which one is finer? The smaller is finer. So the larger it is, it means that you have more retained. So that's kind of the trick here, and that's why I wanted you to pay attention. It's retained. This is how it is defined. So it's actually coarser. If it is larger, it's coarser. It's called fineness modulus, but if it is larger, it's actually coarser. Okay. What happens when we blend aggregates together? So if you blend, which happens very often, if you blend aggregates from several sources and you want to obtain the gradation, you have to use this linear combination. So for example here, let's look at this example together. So we have a specs on the top. So for concrete mix design or asphalt concrete mix design, you need to make sure that your blend falls into these specs. For each sieve, you see what is the percentage passing a range. You could just work with the range, or you could define a target gradation that, for example, here it's looking at the medium number in between, the target gradation. So we have the gradation of A and of B. It's written in this horizontal line. So you see person passing of A, person passing of B. And then we are considering a blend which has 30% A plus 70% B. So looking back at the formula, this is like this, a small a small b. Right? So to get the blend, you basically have to calculate, multiply 30% by the person passing of one and sum it up by 70% of the other, and that's how you get it. For example, we just look at one here, for example. We have 30% times 71 plus 70% times 14. And the first number is 20.3, and the second is 9.8, and then you get 31. You can very easily do this in Excel. Program it so it's very easy. So in the homework problem, I don't want you to use any fancy method, whatever is in the textbook. Just you use trial and error. You can change the percentage such that at the end your blend falls within the specification. So the specs has an upper limit. You see, for example, for this one, the upper limit is 40%, and the lower limit is 20. So when you get 31, it is okay because it falls between 20 and 40. If it wasn't, then you need to change the percentage until it does. It's trial and error. I don't expect anything more than that for the homework. I sent an email to clarify that because there were plenty of questions about that. Is this clear? Do I need to explain this more? Okay. Related problem is how to calculate the composite properties. For example, how to get the composite specific gravity. I told you sometimes we use also G. I like to write this more like that. I think it's easier for me to memorize it. So for a specific gravity, if you have fractions P1, P2, P3, so these are volumetric fractions or weight fractions. And the first one is a specific gravity is G1, G2, G3. For the blend, the specific gravity is obtained like this. For the other parameters, you just use a linear relationship. So this is again, Pi is weight fraction of aggregate I. Now, if you want to look at coarse or fine aggregate, then you use the coarse or fine fraction. That's the small pi for. So if a property is just defined for coarse or fine aggregate, you also have to take into account the percentage or the weight fraction of just coarse or fine in that aggregate pile. Let's do a small example. So look at the example on the next slide if you are done writing here. And once again, if I see a cell phone, I have to ask you to leave the class. I don't know, I don't have this problem in the morning section, but here I'm not sure why the classrooms are not being respected. I know it's similar to one of the homework problems if you have done it already, but try just to do it. Write down the equations one more time. So the first one is asking about composite specific gravity. I like it better this way, but .58. Does it have a unit? No. Part B, what is absorption? What is it? Remember from last time? What is this absorption? 0.4%, 5.2%? Absorption is moisture content at saturated surface dry condition, right? Remember last time? And it is in percentage. So it is a kind of moisture content at the end. It's just for saturated surface dry. That means that the aggregates cannot absorb more water. They are just at their capacity. So the composite absorption this is just a linear combination. And this is about 3.3. Okay. Now, there are a number of tests which are being used to measure the strengths and durability of aggregates. Starting with the strengths. Concrete and asphalt concrete, they get their strengths from aggregates. So they cannot be stronger than the aggregates that make them. There are ways to measure the strengths of the aggregates. You can measure the strengths of the rock. You just drill a core from the rock, measure the strengths, or you look at the bulk aggregates in a triaxial cell. We don't look at the details of any of these, but it's kind of I want to give you an overview. And resilient modulus test is being used for asphalt concrete. You are doing some strength test in C337, I believe, right? Is it just compressive strength? Do you do any flexural bending test? No? Not yet. Any triaxial? No? Confined? Unconfined? Confined. Okay. Great. Another important test is abrasion, because for aggregates it matters that, let's say if you're using them in pavement, especially for asphalt pavement or concrete pavement, you want to make sure that they don't crush under the load of the trucks. So you test that in kind of a simulated way. You have a drum, this blue apparatus is a drum, and there are lots of steel balls inside. So you put the aggregate inside about 5 kilos, and basically you let it rotate. And before you measure the retained weight by a certain speed, and afterwards you measure the same retained weight on the same speed, because we want to see how much of the aggregate is now going through the speed. We want to see how much is actually crushed. And this is mass loss. And typically you don't want to have more than 50% loss. It doesn't matter that you know all the details, but you kind of have to know what types of tests there are, what is the purpose of each, and have a general idea of each one of them. Not all the details, everything, no. Another important test is for measuring the durability during the weathering. So you want to see how much the aggregates are resistant, for example, to freeze-thaw damage. You see how the weather looks like here, for example, how on Saturday the weather was pretty nice, right? And this morning we woke up and everywhere was snow. So when you have cycles like that, you are going to have a lot of damage in, let's say, concrete, which is exposed to this kind of weather. Water goes in, it freezes up, it crashes, and you go through these cycles throughout winter. So to simulate that, you don't want to wait for the whole winter to see what is going on. So you have an accelerated test. You soak the aggregates in a solution of sulfate. So sulfate creates some crystals inside the aggregates, which works a little bit like ice crystals and simulates this kind of damage. And again, you measure the mass loss. You want to see how much of the material is going to be damaged after several cycles of repeating this test. Yeah, that's called soundness test. Yeah, there is a ASTM standard. If you have any questions, just ask me. I go through them pretty fast. Another important feature is in some materials, let's say they contain organic substances, they have excessive amount of clay. This is not something we like because, for example, when you have water, they lose strength. So you want to know how much of these kinds of materials you have, and there are some tests, for example, sand equivalency tests that you can do to find out the amount of clay. Do you do any of this in CE337? No. What do you do in CE3? I never taught this class. Another important test is to measure the alkali activity of aggregates. One of the biggest problems in concrete is something which is called ASR, alkali-silica reaction. This can happen very early on, causes this kind of cracking, and then you have to replace the whole thing. In Germany, once they had to replace the whole section of Autobahn after 2 years because they weren't careful in selection of materials. So you need to find out if your material contains excessive amount, it is alkali reactive. And there are several tests that can be used. The ASTM numbers is given here. You normally look at expansion. So you make a small kind of, we call them cigarette type samples, and you look at how much they expand inside a certain solution. And that's how we find out whether there is reactivity or not. And for asphalt concrete, there is a test which is important to find out whether the aggregates are hydrophilic or they are hydrophobic. And this is important because if the aggregates are hydrophilic, that means they like water, they attract water, then the asphalt fiber that you use, it may peel off from the aggregate. So you have a problem which is called stripping. So the asphalt gets stripped off the aggregate. This is a serious problem, can create you can have pieces of asphalt coming off, let's say in a runway or other truck road. Because if you have a stripping, then it normally happens at a depth of about 2 inches, and then this top layer is basically comes off. So it's an important problem. That's why there are tests to make sure that the aggregates do not have such properties. One thing that we know is, for example, the aggregates which are from limestone, they are less prone to this kind of problem. We'll talk about this a little bit when we talk about asphalt concrete later on. We'll get back to that. And finally, it's important to practice some certain very simple rules to prevent segregation, degradation, and contamination of aggregates. So segregation is that basically aggregates which are similar, they kind of tend to go and make clusters, and it normally happens for rounder and larger aggregates. So typically what you want to do is you want to build your stockpiles in multiple cones, smaller. You don't want to drop the material from a very large height to make sure that this is not going to happen, and you are also not going to break the aggregates. When you are sampling the aggregates for laboratory testing, it's important that the sample is representative of the entire stockpile. So you want to take samples from several locations and mix them up. If you have coarser aggregates, the samples are larger. And one method to use to take samples from larger stockpiles is this quartering, where you get the material, you mix it up, and you basically take 1/4 off, as you can see in this figure. So you make a half, you make the half, and then you take 1 part, and that's what you take to the lab. So the idea is that you want your sample to represent what is in your stockpile. You don't want to take just one part from one side of the stockpile which is not representative. And finally, we need to be mindful of environmental impact, economical impact, social impact. In one word, the sustainability of handling aggregates. So, for example, after a pavement or a structure is being used, you typically want to try to see whether you can recycle the material. This is now common practice. You crush the pavement that you are rebuilding to make sure that you can use some of the material that has been in place. And you can use them. Another aspect that we talked about was using the byproducts of steel mills, for example, slag, as a manufactured sand, for example. So there are ways to ensure sustainability in handling aggregates. And there are industry guidelines and government regulations which are becoming more and more important, and engineers need to take them into account. So now, to summarize aggregates, what you need to know from everything you have learned is basically the difference between coarse and fine natural manufactured materials, understanding the size and shape, and also why they matter. So the homework problems are just questions, but there will be always questions from the material that you are seeing. And this is a good way to know if you know everything in the packet very well. We talked about different moisture states. I hope you remember those diagrams, those cartoons: oven dry, air dry, saturated, surface dry, and moist. Those are very important. How to calculate specific gravities, absorption capacity, this is what we learned last time. Gradation, this is what we learned. The shape of the gradation curves, if it is gap graded, if it is open graded, etc. You need to be able to interpret the shape of the gradation curves. Calculate the composite properties of mixed blends. This is what we talked about today. And have some overview of different test methods that we use to measure the strengths and durability of aggregates. And here are some of the buzzwords and technical terms that you need to know. If you don't know, you always have to go back to the notes, find them, and then use them. So I guess I just put them in 2 piles. I don't know how order. So from A to K and L. So Please look over your exams and let me know if you have questions in the class today. Cannot come back after 2 weeks and tell me, no, well, you haven't seen this or that.